I want to show you different sky models. So this was a realistic simulation in the sense that we took a realistic sky model. It was actually a catalog. Something that can be a lot more interesting in terms of just exploring the system and exploring, interferometry and visibilities and all that, is to have synthetic sky models. For example, just a single point source. And you can do that through this option here, the gridded sky. So, for example, gridded sky can be used to make a grid of sources. So I'll show you how to set that up. Let's make, for example, a 5 by 5 grid. So we're saying we want a 5 by 5 grid. We want them to be 30 arc minutes apart. And we want the sources to be 1 Jansky. And maybe we want the central source to be 2 Jansky. And no polarization, no offset, so just something like this. You don't have to do it exactly this, I encourage you to play an experiment here. Because this is the way to really understand visibilities and interferometry, is to play with these kinds of synthetic little models and see what sort of visibilities they produce. But for the rest of it, it's exactly the same, right? So the only difference with the previous simulation is that we've unchecked the Tigger sky model and we have checked the gridded sky model. That's the only difference. And also I'm going to turn noise back off, because if you're going to do, if you want to do toy simulations to learn things, you probably want to do it without noise. So now let's open a bookmark for the inspector. So you can see that the resulting visibilities are completely different, of course, because we have a different sky model. And then if you make an image, well, indeed, you're going to see a grid of sources. And the central source is a lot bright. Well, we put in 2 Jansky for the central source and 1 Jansky for these guys. Now, to make it even more, to make it even simpler, we can just go to 1 source. So if you say a grid model composed of just 1 source, there's going to be 1 source at the center. It might be a little bit boring if it's at the center, so we can offset it by 60 arc minutes, for example. So this is like almost the simplest sky you can simulate. Now, in fact, it's so simple, it's making the inspector behave funny. Oh yeah, of course. It's not yeah, of course, yeah. So it's a single source. So what is the visibility of a single point source? Right? If that single point source is at center, well, perhaps we should make it even simpler and put it at the face center. Then, yeah, it's completely flat. And there's many ways to understand this, right? You can think of the source being in the middle between your two antennas, so the phase difference to all the baselines is to all the dishes is completely the same. You can think of Fourier theory. What's the Fourier transform of a delta function at 0? It's just flat, it's a constant. So that's what you're seeing in the inspectors. You're seeing a flat amplitude and a flat phase, right? It's just a constant. So this is a source at center. Now if we offset the source a little bit, let's start small. Let's offset it by like 5 minutes. So it's still a constant amplitude, but if you look at the phase, see what the phase is doing? So the Fourier transform of an offset delta function is a constant amplitude and a gradient in phase, right? So your UV plane looks like constant amplitude, gradient in phase, and your baseline, each of your baselines is making an arc through that Fourier plane, right? So basically it's sweeping out an arc along the gradient in phase. So if you look at the visibility on each baseline as a function of time, what you're seeing is the phase changing along that arc. And you can see that for the longer baselines, such as 1,6, so you can immediately see that like 1,5 is a longer baseline than 2,3. Because for baseline 2,3, the change over the observation is very little. It's a short baseline, so it hasn't swept out much. And for a long baseline, such as 1.5, the thing makes more of an arc, right? Another thing you can do with these plots, which I forgot to show you, is you can lift them out by middle clicking. So if you middle click on any one of these tracks, you get kind of a zoomed in plot of that particular track. And then it's a combination real imaginary. Using right click, you can look at it as real imaginary or amplitude phase. So this kind of shows it very well here, right? You've got a totally constant amplitude of 2, because that was the brightness of the source that we put in, and you've got a change in phase. And so now, for example, we can go back and make the source. It was only 5 minutes from center. We can make it 60 arc minutes from center. And you can probably guess what you're going to see now if you're on the simulation. Again, it's a constant amplitude, but you can see the phase is now changing a lot faster. And that's because the source is far, it's a delta function that's much further from 0. So it has a bigger phase slope. And then, well, another nice thing to try is make a really bright source in the middle, say 5 Jansky, and put 1 Jansky sources on the periphery. And don't make a grid of sources, make a bar. This is basically 3 sources in a line. I'll make an image immediately to show you what kind of sky model we put in. So what we've got here is 1 source in the middle, a bright one, and 2 fainter sources off to the sides of it. Right? Now look at the visibilities this produces. I've got a sky model that's called L-bar model. L from the L coordinate. So it's a line of sources along L. 3 sources in each direction, and I've put 5 Jansky for the central one and 1 Jansky for the ones on the side. So this is always an interesting one to think about, right? Why do my visibilities look like this? Right? And the way to sort that out in your head, I think, is to think of the complex plane. So just concentrate on one baseline for now, right? So this is the complex plane, real and imaginary. We have a bright source in the center. A bright source in the center is a constant visibility with no phase, right? So that will be a long this is your first visibility component corresponding to your first source in the model. Now on top of that you have 2 more sources which are off-center. So they're going to be constant amplitudes but rotating phases. And because those 2 sources are on opposite side of the central source, they're going to be rotating in different directions. So you've got something like 1 vector here, maybe another vector here, and essentially you're taking the vector sum of So you can kind of think of these visibility vectors as being attached to one another. And this one stays constant because this source in the phase center. And these sources are offset, so their visibility is rotating. So the resulting sum is going to be this long vector which kind of goes, funny patterns. And that's exactly what you see on the plot on the screen here.
What is the red and the green?
Amplitude and phase in this case.
Amplitude and phase.
Yeah.
You have 1, 2, 1. It's basically 1, 1 that's involved with each other. So it would be like a cross square in some sense.
1 to 1. What do you mean?
So you have 2 impulses in the first unit cross. One impulse is e to the j, unit cross, and you have 3. 1, 2, 1, it's basically a unit cross square. So I guess it's because those arrows add up. So basically add up to the real line.
Why don't we check if that's true, actually? So let's do 1 to 1. Is this what you expected?
In my case, I get the real and the magnitude are very similar, so the imaginary is quite small.
But this is amplitude and phase.
Okay.
So if I look at real and imaginary, no, this is real and imaginary. Sorry, this is amplitude and phase. Yeah, this phase is actually even funnier. It's got these little bursts. Okay, so that's something you can use to sort of, learn about visibilities and things like that. I propose we look at another one of these simulations. But perhaps not number 2, because number 2 is, it's about calibration, and calibration we don't cover until tomorrow. But number 3, right? So simulation number 3 in the list deals with the effects of the primary beam. And the primary beam, as you remember from Rick's lecture, is basically the sensitivity pattern of the antenna, right? So in the previous simulation, we had no primary beam at all. In that simulation, we kind of pretended that the sensitivity of the antenna was totally flat, that it was receiving, the same signal from the whole sky. Of course, the real antenna isn't like that. The real antenna will have a beam pattern, so it's going to have a main lobe where it's maximally sensitive. It's maximally sensitive, down the middle, and then sensitivity falls off, and then it's going to have side lobes. So what Ian suggests next in these simulations is actually adding a primary beam, just to see how to simulate that. And again, there's a lot of text which you can read at your own leisure. So here's what we should do. We should go back to options and go back to our realistic sky model, right? And now it's time to look at what else is on the screen. So you can see there's different instrumental effects that you can add to your simulation. And one of them is called use E-Jones. And well, I talk about Jones matrices tomorrow. For now, I should just tell you that E-Jones is what we call the primary beam. So the E-Jones matrix takes into account the effect of the primary beam. So what you should do is enable that option. And there's a whole bunch of beam models in there. And most of them are actually a pain to set up, but the first one is very simple. So if you select the first one, analytic beams, and this is basically a simple beam model that has traditionally been used for Westerbork, which is basically a cosine to the third of distance from center. If you've done any Westerbork data, you will recognize this cosine to the third thing. And there's a few parameters that go into the beam model. Well, basically this determines how big, this is like a magic constant which determines the size of the beam, which we know for Westerbork is about 65, so we'll just leave it alone. This is the interesting one, this is the dish size. So cosine to the third is for a 25 meter Westerbork dish. So if you want to get some approximation of a Cat 7 dish, a very simple approximation, we just have to rescale the beam to the different dish size. So change this from 25 to 12. And then the other parameters we can probably leave alone for now. There's another useful option to set, and this is just to make the simulation run faster. Basically, you can tell it that you want to use the same beam for all the stations, which makes sense in this case because we just have this analytic model which we're going to apply to all the antennas equally. So under advanced options you check use same E-jones for all stations. And I think that's pretty much it. Once you've got this set up, you can compile it. Run the simulation. So your squiggly visibility lines look a little bit different. If you recall what they looked like before. So something is certainly changed in our simulation. To really appreciate it, you should go and make yourself an image. So this is the new image we've generated. Now the way to look at it is to compare it to the previous image, right? You have this is why another reason why I told you to copy the first image we made with the original simulation. So if you load the two images into Tigger, and if you lock the color scales together and blink between them, if you want to increase the contrast, enter something like 0.5 here. I think this is a very neat demonstration of what the primary beam does to you, right? So this is the original simulation where we didn't have a primary beam at all, where we just had a flat pattern. And this was the brightest source in the simulation. It was even brighter than the central source. And in the simulation of the primary beam, you can still see it, so it's still there. But it's been attenuated down by the primary beam to very low levels. Whereas the central source and the sources around here, they've really barely changed. And for another comparison, let's say, just as a mental experiment, what if we change our dish size to 6 meters? What's that going to do? So I'm going to rename the image. This is the image we made here. I'm going to call it Sim1, 12 meters fits. And I suggest you run another simulation where you change the beam size to 6 meters. And challenge yourself to predict the outcome. I'm not going to show the image yet, so you can think about the outcome while you run your simulation. Okay, has anyone got a 6-meter image? Okay, was it what you expected? Did it meet your expectations? So this is with no beam, this is with a 6-meter, the 6-meter dish. Well, it's quite clear what's happening here, right? If your dish size goes from 12 meters to 6 meters, the beam pattern basically blows up by a factor of 2 instead. So whereas in the 12-meter simulation the size of the beam was just about the size of the image we made, in this simulation the size of the beam is much larger, so the sources are not attenuated quite as much. Well, basically your beam size scales as a function of frequency, right? So if this is the beam for a 12-meter dish, right? Then the same similar dish, but of 6 meters, is going to have a beam pattern that's essentially twice as wide, right? So the main lobe is going to be the green one and not the red one. So the same source, it's not going to affect the central source because the central source is still sitting there at maximum sensitivity. But for that bright source off to the side, you can see that at 12 meters, the beam has fallen off a lot more than it has at 6 meters. And if you want to check this, you can go in another direction, go back to a 25-meter dish. And then you should only see, you will really only see the central source left, and all the ones on the periphery are going to drop down. Okay, so this is something you can play with. Another so another really interesting simulation is number 4, actually. So if you get tired of playing with the first, avoid number 2, save it for tomorrow. But if you get tired of 1 and 3, try number 4. And number 4 is where essentially we are simulating a transient source. So the problem with transient sources is that, when we talk about interferometry and sampling the Fourier plane and Fourier transforms and all that, you're kind of implicitly assuming that the sky is stationary, which most of the time it is. But if you're interested in transients, then you're actually interested in the things that go pop in the middle of your observation. And it's kind of actually quite counterintuitive what that does to your data and what that does to your images when you have a source that's sometimes there and sometimes isn't, while you're filling up the UV plane. So it's kind of difficult to understand what's going on, but with simulations like this, you can sort of at least figure out what it does, right? So what I recommend is you load the same simulation script. Keep the beam pattern in, but make it 12 meters instead of 6, as we did the first time. And so what we can do now is we're still using the same sky model, but we're going to add a transient source to our sky model. And you can do that in this simulator by clicking this transient sky thing. And what this thing essentially simulates is a source, is a variable source that goes off with the Gaussian light curve. Let's have a rummage around in Ian's document to see what sort of settings he suggests for this. So he suggests a transient model. These two parameters control where, relative to the start of the observation, the flare in the source actually happens. So he is using 7200 seconds, so a couple of hours there, duration of half an hour, and the flux of 3 Jansky. So essentially what he's suggesting is that we add a transient source that flares for half an hour to a brightness of 3 Jansky. Again, it doesn't really matter that you get the exact same thing as I do. But try your own, play with your own. And so now if you run the simulation, actually if you look at the visibilities inspector, you can already see where the source is going off, right? All of the visibilities have this little bump. So that's where our transient source was flaring. And then if you make an image of that, well, who can spot it? That's the question. What we did was we made, the transient source was in the center. So essentially what we did in the simulation, we made the central source flare up for half an hour. Right?
There's two blobs on the top and bottom.
Yes, exactly. These two blobs were in 34. And this is why I've been telling you to rename your images. So if you go back to our 12-meter simulation, so if you blink between this image and the image we made of a, of the nominal sky where nothing was flaring, you can see the difference, right? And if you use the image arithmetic option, you can actually extract the, the pure signature of this flaring source, and that's what the pure signature looks like. So this actually isn't very good news for us, right? Because you think, okay, you've got one source flaring in the center of the image, that's where you would expect to see the structure. But you're not only seeing that extra structure in the center of the image, you're seeing all this crap. And the way to understand this crap is you can think of, think of your instantaneous UV coverage. Think of your instantaneous PSF. For all the normal sources, the instantaneous PSF, you kind of see the average of all the instantaneous PSFs, and they all combine into a nice looking source. Now, for the source that flared, you're seeing this instantaneous PSF that was going along, and then it boom, produced those little peaks there, and then went back to being a normal PSF. So this sort of thing is what makes the transients business very interesting from an instrumental point of view.
There is one flare, or there is a periodic flare?
There's one flare, but we can in Ian's Perlog it actually shows you how to add more. You can add a second flare.
So yes, this is a snapshot PSF at this time.
Essentially, when the source flares, you get the garbage that's left in the image is essentially the snapshot PSF for that half an hour while it was flaring. Anyway, I think that was all I was going to show you for today. What I'd like you to encourage is to play with this if you're interested. Change the options, see what it does. I hope I've given you enough to get you going. And hopefully, together with Ian's explanations, you can actually run this thing on your own so a little bit. Any questions? But it's, what's the update? Yes, you're still in between runs. Yeah, what happens here, the bookmarks are a bit. Because what happens is the nodes underneath change. So if you want to save, it goes over. Essentially, if you change a lot of options, it tends to break the bookmarks. So basically, you just need, just identify by essentially.
That's no problem. You've only got one measurement. One measurement, see the difference.
Well, that's the problem. Because what they actually do is it's not really that's principle you should be able to have a long
Using one long.
Yeah, usually like so because then you have a less sensitive to the smell. So hopefully because of that, these crabs instead.
Observation, kind of break that into say 3-4 hour observations and try and see somewhere there if there's a spike. Because then you've got say 3-4 hour ones which might have lower sensitivity but is high enough. Then you can keep breaking it down into okay fine. We found in some of these sections we found something more than other times. So then
Yeah, I suppose you could do that. But then to track the thing down, you have to keep bisecting it anyway until you get to these low numbers.
But
Then you end up looking at some approaches.
yeah, but the thing is, at least if you do it the other way around, stop knowing there's something there, it's not an artifact. Because if you start just at snapshots and you don't know it's an artifact, you keep looking.
But that's what interesting is. We kind of work with it, so, like, for example, this in the thing is a start. What we want to do is we actually want to expand it to 7 illustrations. That's what you're saying about it. It's, you know, problem is, you know, so few about so much.
What's the timetable from now until?
Ooh. How beautiful. Thank you.
Was the concept Okay, folks, there's no dinner organized tonight, right? So you're on your own. You can have dinner in the hotel. It's not very expensive, and do like a dinner buffet or something, I think. Or there's an information pack in your room with places to eat around town. So you're kind of, you know, we figured you'd be getting sick of each other's company at some point, so you need some time to do your own thing. And it's 5:30, so I declare the session officially over.